Okay, so we're given this polynomial, fourth degree, and we're asked to find the best integral bounds on real zeros of f. Now, integral means whole numbers. We're not going to be messing with fractions here. We're just looking for the best upper bound and the best lower bound so we can put a restriction on what the zeros could possibly be. So let's go with step one. We are going to find the upper bound. Okay, so we're going to start by synthetically dividing by integers, whole numbers. We'll start with 1, then we'll do 2, then we'll do 3. Now we're looking for an upper bound, so what we're hoping for is that we get all non-negative results on the bottom of our synthetic division. And remember, zeros can count for either sign, whichever is convenient for us. So let's set up our synthetic division. And let's write the coefficients. First we have the coefficient of x to the fourth, that's 1. And then the coefficient of x to the third, which is missing, it's 0. Then the coefficient of 2 of x to the second is negative 3. Coefficient of x to the first is 2. And the constant coefficient is negative 5. We're going to synthetically divide by the number 1. Leave some space, make a line, bring down the first number 1. Multiply. 1 times 1 is 1. Add, you get 1. Multiply. 1 times 1 is 1. Add, you get negative 2. Well, you can stop right there because we're looking for something where we synthetically divide and the result on the bottom is all non-negative. That messed it up for us, that negative sign, so we're ready to go on to our next try. For our next try, we'll step over this to the left and we'll synthetically divide by 2. Divide the same coefficients as before. 1, 0, negative 3, 2, negative 5. Leave some space, bring down the first number, 1. Multiply. 2 times 1 is 2. Add, you get 2. Multiply. 2 times 2 is 4. Add, you get positive 1. Multiply. 2 times 1 is 2. Add, you get 4. Looking pretty good. We want all non-negative on the bottom. 2 times 4 is 8. Add, you get positive 3. Great. Okay, I'm going to put a big balloon around that because that's really cool for us. These are all non-negative. And that means, since we synthetically divided by a positive integer, that implies that a equal the number we divided by is an upper bound. And it is the smallest integral upper bound because we started with 1, then we would have gone to 2, and if that hadn't worked, we would have gone to 3, 4, until we got the one that was closest to 1. Okay, but there's something, even though that it is an upper bound, unfortunately, it's not a 0. And how do I know that? Because if it were a 0, in other words, a root of the polynomial, if we set the polynomial equal to 0, a polynomial equation, it would have a 0 remainder, and the remainder here is 3, not 0. So while we found an upper bound, it's not actually a root. Okay? So now let's go to step 2. Step 2 is our search for the lower bound, my bad. We just found the upper bound. Find the lower bound, LB. Doing this, we're going to divide by negative integers, starting with negative 1, and negative 2, negative 3, until we finally get lucky, and on the bottom we have, in this case, alternating signs on the bottom. Then we'll know we have a lower bound. So here's negative 1, where we're going to start our synthetic division, and then use the same coefficients, 1, 0, negative 3, 2, negative 5. Leave space. Write your line, bring down 1, multiply. 1 times negative 1 is negative 1. Add, you get negative 1. Okay, it's looking good so far. It's alternating signs on the bottom. 1, negative 1. Let's hope the next one is a positive. Negative 1 times negative 1 is positive 1. Add, negative 3 plus 1 is negative 2. Okay, wait a minute. We got 2 negative guys in a row. We wanted alternating signs. This messes it up. We can stop right there. It's not going to be negative 1. Let's go over here a little bit to the left, and let's try to synthetically divide by negative 2. The next negative integer. 1, 0, negative 3, 2, negative 5. Make a space, a line, bring down the first number. 1 times negative 2 is negative 2. Add, you get negative 2. Multiply. Negative 2 times negative 2 is positive 4. Add, you get positive 1. Well, this is looking good. We're hoping for alternating signs. We've got 1, positive 1, negative 2, positive 1. Let's continue. Multiply negative 1. Negative 2 times 1 is negative 2. Add, you get 0. Okay, now is that going to work for us? Yeah, that's going to be okay because remember, zeros can count as positive or negative as we want it to. So we've got positive 1, negative 2, positive 1, negative 0. We're counting it as a negative. Let's multiply. Negative 2 times 0 is 0. Add, we get negative. Uh-oh. We went from a negative to a negative, right? We didn't alternate here. Positive 1, negative 2. Positive 1, negative 0. Negative, no. Another negative. That messes it up. Let's try the next negative integer, which would be negative 3. Hopefully this will be enough. 1, 0, negative 3, 2, negative 5. Okay, make a space, bring down the first number, 1, multiply. Negative 1 times 3 is negative 3. Add, you get negative 3. Multiply. Negative times a negative is a positive, 9. Add, you get 6. Positive 6. Are we doing well? Positive 1, negative 3, positive 6. Looks good so far. Negative 3 times 6 is negative 18. Add, we get negative 16. Okay, that's great. Now, if we can just get a positive number here, we'll be where we want to be. We'll have alternating signs. Let's give it a try and see what happens. Negative 3 times negative 16 is positive 48. Minus 5 is positive 43. Great. We got it. Because see the bottom here? The bottom alternates signs when we divide it synthetically by a negative integer, whole number. Okay, so that means that right here, that means, so I should say alternating, so we'll remember alternating signs. And that implies that A equal the negative 3 out here in the front is a lower bound. I'll put that in the box, and I'll note something also. This is not a 0, again, but not a 0. You're saying, why do you keep saying that? Well, again, I ended up with a number at the end, which is considered the remainder at the end, and it's not 0. So that means it's not going to be a root, but it's going to be a boundary on the root. Here's our conclusion. Thus, let's see, our upper bound has to be less than our x root less than our lower bound. That's where we're going. And the reason I put less than instead of less than or equal to is because in both of these examples, we didn't get a 0 remainder, which means these are not actually equal to a root. They're just a boundary on the root. So that means for this problem, we found positive 2 is our upper bound, less than our roots x, less than negative 3, our lower bound. So this inequality is the bound, B and D, on real zeros. Okay, what does that mean exactly? That means that when we find the roots of this polynomial, which we're not going to do here, we're not solving it, but if we found the roots of this polynomial equal to 0, we would find numbers between 2 and negative 3. You know what? I got that backwards, didn't I? The negative number goes on the left side. Okay, forget this. Let's fix it. Negative 3 less than x less than 2. This is a great smart pen, but it doesn't have a smart eraser.